Hello everyone, I'm finally back with another video, and this time I will share my learnings of implementing a graph variational autoencoder for molecule generation. The last weeks I read a lot of papers and tried out different approaches. My goal is to compress everything into this video, and I hope that others can use it when getting started with this topic. In the last video I focused on the reconstruction of the adjacency matrix of the molecule graph. To do so, I had a separate latent vector for each node. This means I output separate means and variances and sample from these distributions independently. Now that, however, is not too useful for sampling new graphs. The reason for this is that I don't have a graph level latent vector, but instead several node level latent vectors. The information about an input molecule is therefore distributed. Node-level latent vectors are not really what we want, as they contain no global information about the molecule, so its structure and connections. Sure, then let's output only one latent vector by the encoder and use it for the sampling. And that is where the difficult part begins. How do we map back this individual vector to a graph? This decoder part is the real difficulty for graph variational autoencoders. Especially now that we want to reconstruct the whole molecule and not only the adjacency matrix. There are three problematic aspects we need to consider when building one-shot decoders. First of all, we need to output graphs of different sizes. If we would use a fully connected neural network that predicts the adjacency matrix and the nodes from this single latent vector, the number of output neurons would need to be different for different sizes of graphs. I will mention a couple of solutions to this problem in the next minutes. The second problem is that it might be the case that the decoder predicts a different number of nodes compared to the ground truth. This makes it difficult to compare the input graph with the reconstructed graph, as they have different shapes and we cannot easily calculate the loss. The third problem goes in a similar direction and is the most challenging one. We totally lose the node ordering when encoding into the single latent vector. Graphs are isomorphic and different orderings still represent the same data. However, the decoder only outputs one specific ordering and we cannot guarantee that it matches the one of the input graph. Therefore, it would be necessary to compare all possible permutations of graph orderings, which is simply infeasible for larger graphs. In the following, I quickly want to present a couple of papers on one-shot decoders and explain how they cope with these problems. One additional comment: all of these three problems were not the case for the adjacency reconstruction from the last video, as we encoded each node individually and therefore maintained the node ordering as well as the graph size. Let's start with the paper Graph VAE from Simonovsky and Komodakis. Their decoder is a fully connected neural network that outputs an adjacency matrix, a node type matrix, and an edge type matrix. That's all information that is required to reconstruct a molecule. How do they handle the three mentioned problems? First of all, they specify an upper bound k on the graph size and output the matrices with k nodes. This means we have a fixed output dimension for the neural network, but also allow the model to predict smaller graphs by simply predicting no node. Now, what about the calculation of the loss? How is the reconstructed graph compared with the input graph, and what if the sizes are different? For this, the authors use a graph matching algorithm to find the correspondences between two graphs. This also solves the third problem, which is the node ordering problem. This matching algorithm is called max pooling matching and was proposed in a computer vision paper called Finding Matches in a Haystack. It has a polynomial computational complexity and is therefore a problem for larger graphs. So overall, the architecture is pretty simple. The input graph is encoded into a latent vector where we sample from, and then we use a fully connected network to output these three matrices on k nodes. And from these matrices, we get a graph which can be used and applied to this graph matching. The second paper I had a look at is called Two-Step Graph Convolutional Decoder for Molecule Generation. Here the molecule is encoded into a single latent vector and then two steps are performed to recover the molecule. The first step is to predict a molecular formula, which means the number of atoms per type, and this is called a bag of atoms in the paper. This can be achieved by a fully connected network that outputs a matrix with the counts of each atom type, and the rows stand for the number of atoms of that specific type, and after applying softmax, the row with the highest activation is selected to generate this molecular formula. So in this example, with only ones and zeros, for simplicity, it will lead to CN3, because we have one C atom and 3 N atoms. The second step is to create a graph input for a GNN decoder. This graph is constructed from the molecular formula which was predicted in a previous step, which means each atom in the formula corresponds to a node in the graph. As no edge information is available at this point, the graph is simply fully connected, so each node is connected to each other node. The node features of the graph are constructed by the latent vector, the atom type of the nodes, and finally a positional feature that allows to distinguish atoms of the same type. Then this graph representation can be passed through a GNN, and the final embeddings can be used to predict the edges between two nodes. Finally, they perform also a beam search to improve the validity of the molecules. So that's the rough structure. Now let's check how the previously mentioned problems are solved here. What I like about the paper is that they have an actual GNN decoder which can handle graphs of arbitrary sizes. The only thing that is required is an upper bound on the molecular size for predicting the molecular formula. So this is similar as in the last paper. Now, what if the predicted molecular formula has a different size than the ground truth? I tried to implement this paper but found no reasonable solution for it, as there is no node matching performed. Unfortunately, there is no source code available for this paper, so I'm not 100% sure what's the solution for this problem. But I read in the paper that they train on molecules of the same size, so it might be related to that. Finally, an explicit graph ordering is enforced by converting the produced molecules to a canonical smiles representation. Different orderings of the nodes will always lead to the same canonical smiles string, and this allows to compare molecules. Overall, I like the ideas of the paper, but there were quite some open questions when implementing this. For example, the positional features are also calculated based on canonical smiles. However, I think it's not possible to calculate the canonical smiles without having edge information. Furthermore, what happens if the canonical smiles cannot be calculated because a predicted molecule is invalid, which is always the case in early epochs? What should be used as a loss value then? Another interesting paper I found is called Permutation-Invariant VAE and was published just some month ago. As I said, the biggest pain point of graph VAEs is the isomorphism problem. It would be necessary to have a model that is invariant to permutations of the graphs. This work attempts to solve this problem by additionally learning a permutation matrix. So if the ordering of the input molecule changes, the model would be able to detect this and apply a different permutation to rearrange the reconstructed output. This is one of my favorite approaches because it feels like it's the machine learning way to solve this problem. The permuter model takes the output of the encoder, so the embeddings of each node, and predicts a score that corresponds to the probability of having a lower node index in the decoded graph. With these scores, the soft sort operator is applied to derive a permutation matrix that sorts the nodes. Positional embeddings are created just like in the NLP transformer model, and they are rearranged using this permutation matrix. This finally leads to positional information that can be combined with the sample latent vector. The decoder is simply another GNN that performs a couple of message passing steps, and then the node and edge properties are predicted with fully connected networks. The nice part is that the permuter model is detached from the decoder, so during inference it's not required to apply a specific permutation for the generated molecules. You might already wonder where GNN layers are used here. The authors use something similar called a message matrix. The relationship between nodes is represented by these calculated messages, which are just constructed by the two node feature vectors and their connection. It's just another way to represent a graph. Now, the key idea here is to apply the attention mechanism in message passing similarly as it is done in papers like the graph attention paper by Veličković et al. Therefore, different graph sizes can easily be handled as the ideas of graph neural networks are used both in the encoder and the decoder. The message matrix has a fixed size and smaller graphs are simply padded with disconnected empty nodes. So in fact they also use an upper bound on the molecule size similarly as all the previous papers did. Regarding the calculation of the loss, I didn't find too much information, so I'm not sure what happens if the decoder predicts a graph of a different size than the input graph. My assumption is that it has something to do with this padding and they simply always compare only the nodes that are not empty. Finally, the node ordering is learned by this permuter model, which is a quite elegant solution. Unfortunately, there is also no source code available and it probably takes some time to implement this as there are many tricks which might not be mentioned in the paper. The last paper I want to highlight here is called Efficient Learning of Non-Autoregressive Graph VAEs. In a nutshell, what the authors propose is to not directly compare the reconstructed graph, but instead only approximately. This approximate reconstruction loss compares the following things: the number of atoms per atom type, the number of edges per edge type, the number of atom-edge pairs, and finally the number of atom-edge-atom pairs. This reminds me a bit of calculating a couple of handcrafted graph descriptors and using them to compare the input and output graphs. This loss function is then permutation-invariant as the sum is used in every term. With this simple trick they state to generate smaller molecules with up to 55% validity. Using further things like reinforcement learning, they were able to get 90% valid molecules. The new graphs are constructed by using a simple fully connected neural network that outputs atoms and edges similarly as it's done in the first paper. The previously mentioned problems are then solved as follows. They define an upper bound on the graph size and choose a fixed output dimension for the fully connected network. For smaller graphs, the model can simply predict empty nodes. If a differently sized graph is reconstructed, it's still no problem to compare them as this approximate reconstruction loss is used. Same goes for the ordering because this loss function is permutation invariant. As I like the simplicity of this last paper, let's take a closer look at how this can be implemented. The encoder is pretty simple and just converts the molecule into a latent representation. This can be achieved by a couple of GNN layers and then a final pooling operation that creates a graph level embedding. The decoder then uses a sampled vector and now simply connects it with a couple of fully connected neural network layers. The network splits in the end and outputs two things. First of all, the node information in a matrix. The dimension of this matrix is the upper bound on the graph size n times the atom types including the one for no atom. Secondly, the upper triangular part of a three-dimensional tensor is predicted. The dimensions are also the number of nodes times the number of nodes, and then a third dimension with the different edge types such as single, double or triple bonds. And with these two outputs we have all the information we need to construct a graph. Using the approximate loss function we can then tell the model how close it got to the original graph. As you can imagine, this model has a large space complexity and therefore it's only suitable for smaller molecular graphs. So I hope this little overview was helpful for some of the viewers. My personal feeling is that graph VAEs might not be the best architecture for graph generation because generative adversarial networks, for example, don't require to compare two graphs as they don't suffer from this node ordering problem. Also somehow graph variational autoencoders speak against the initial motivation of GNNs. And this motivation was that they allowed to handle dynamically sized and unordered data for machine learning. But some of the papers use fully connected decoders and with that lose all of the permutation invariance advantages because they leave this graph domain. These 4 papers I presented were just some examples for literature on generating molecular graphs. For this series, I decided to implement the paper with the approximate reconstruction laws and already achieved to fully reconstruct the atoms of several molecules. Regarding the edges, however, I didn't have too much success yet, and it still requires some tweaking to make this work. Anyways, I've uploaded all of the code to GitHub in case someone wants to play around with it. Overall, I have to say I a bit underestimated the efforts required to make this work, and I think most of the implementations are the result of several years of research. Therefore, it was probably a bit too ambitious to get this fully working within a couple of weeks. So the next video will be about the model deployment in Streamlit. Thanks for watching, see you soon in the next video.